So our second speaker in the second Wednesday session is Natalie Paquette, who's in some state between Caltech IS and University of Washington. And she'll talk about twisted holography and Koszul duality. So thanks, Natalie. Please go ahead.
Thanks very much. And I want to thank the organizers for inviting me to this conference and for putting it together during this difficult time. I wish I could, of course, see all of you in person, but hopefully we'll be able to do that soon. So today I'll be connecting some toy models of the ADS-CFT correspondence with a mathematical notion called Koszul duality. And this work is in collaboration with Kevin Costello. So I hardly need to tell the attendees of this conference that string dualities are a rich source of novel mathematics or novel connections between different areas of mathematics. And there are, of course, too many wonderful examples to list, many of which have been discussed already at this conference, with, for example, mirror symmetry and its homological enrichment giving one precise instantiation of this idea. But we have an extremely rich physical duality in the ADS-CFT correspondence, from which we're learning a lot about quantum gravity, that I think it's fair to say hasn't yet permeated back to the mathematical community. And I think it's also fair to say that a better mathematical understanding, at least of some special examples of the duality, could be useful for us physically with respect to perhaps gaining some conceptual insights or learning new ways to think about or organize observables. So today, when I think about the ADS-CFT correspondence, I'll have in mind particular top-down models coming from string theory constructions starting in 10 dimensions in the presence of D-branes. And I think the audience is largely comprised of physicists, so all of this is very familiar stuff. But of course, roughly speaking, the ADS-CFT correspondence from this top-down perspective is two complementary ways that turn out to be equivalent of thinking about the same D-brane physics, again, being very cartoonish. So on the one hand, we'll have some stack of branes whose excitations are given by open strings, and in a suitable low energy limit, we have some supersymmetric world volume theory that's a quantum field theory that in our examples will be, in fact, a conformal field theory. And on the other hand, we can look at the geometric background of string or M theory in the presence of these branes. And again, in a suitable limit, we find a closed string geometry, a closed string background or a gravitational theory whose geometry includes an anti-de Sitter factor. So today we'll be trying to really describe some of the mathematical underpinnings of a toy model coming from one of these top-down constructions. So let me introduce now the hero of my talk. There we go. So the dual pair that we're interested in today is familiar, I think, again, to many people in the audience. On the gravitational side, we have type 2b supergravity or string theory in the background ADS3 cross S3 cross T4. And for much of the talk, I will be focusing on the strict supergravity limit where I'll be taking the string coupling to 0. And this is well known to be dual to a 2D conformal field theory, actually a superconformal field theory on the moduli space of the sigma model whose target is the Hilbert scheme of endpoints on T4, with the corresponding dual limit here being the limit that n goes to infinity. And well, closely related to the fact that this target space geometry is hyperkähler, the 2D conformal field theory enjoys two copies of the n=4 superconformal algebra, one holomorphic and one anti-holomorphic. So of course, there's a lot of supersymmetry in the game. And what we'd like to do is to exploit that and do what we often do when we try to make some precise connections to mathematics and study this duality in the presence of a certain supersymmetric twist. So the name of the game will be to start with this very rich physical duality and restrict to some protected cohomological subset of observables that correspond with some BPS observables in the full physical theory. And I'll say more about that on the next slide. And then ultimately, as we study this twisted toy model, we'd like to make some connections to generalizations of a mathematical subject called Koszul duality. So for us, this was a nice example to study for a few reasons. Firstly, it's a fairly technically simple example of ADS-CFT as these things go, in part due to the relatively low dimensionality of the theories involved, a 2D conformal field theory, 3-dimensional ADS space. And it's also been extremely well studied from a variety of perspectives. So as we try to probe this twisted version or this toy model, we're able to benchmark it against a lot of results that have been produced by studying the full physical or untwisted duality. So in spite of its technical simplicity, it's still quite physically rich, but nonetheless, in the twisted version, we have some hope of making some mathematical statements and hopefully gaining some new insights. So what's the twist that I'll be talking about today? Well, the kind of twist that I'll be discussing is a slight generalization of the more familiar topological twists that I think are, again, quite familiar to most people in the audience. So in addition to our usual BRST differential, which we use, of course, to restrict cohomologically to gauge invariant observables, to that we'll add an additional nilpotent supercharge in the theory Q and take the cohomology with respect to this total supercharge Q tilde. And if we imagine, for example, that we're studying a theory, say in flat space, where we view the space as complexified, for example, in 10 dimensions, 5 copies of the complex plane, and we endow that with holomorphic and anti-holomorphic coordinates, then we'll choose a supercharge that has precisely the property the translations in the anti-holomorphic directions are Q exact. And there are natural choices of Q also for the slight generalizations that we'll need. So this twist is often called the holomorphic twist, and it has also appeared in the literature in a few contexts. So we'd like to apply this twist to both sides of the dual theory and study, to both sides of our duality and study the results. Okay, well, on the 2D conformal field theory side, what sort of mathematical structure might we expect if we perform a holomorphic twist of this type? Well, if we're rendering anti-holomorphic translations exact with respect to our supercharge, or exact with respect to the cohomology that we're interested in, then the algebras of operators will have a position dependence that only depends on the holomorphic coordinates, possibly with some poles as the operators become coincident. And that's exactly the right kind of structure to have a vertex algebra or a chiral algebra on the CFT side, or perhaps something related to the chiral de Rham complex if there's a geometric interpretation in the case of a sigma model. Correspondingly, there should be a dual notion of twist on the supergravity side that we're able to make use of. And for the purposes of today's talk, we'll be making use, we'll be assuming a conjecture of Costello and Lee, a conjecture for which I think there's a good deal of evidence, that describes what the appropriate dual notion of a twist is for the supergravity side, which of course has been a bit trickier historically due to the fact that supersymmetry is gauged in the supergravity theory. But Costello and Lee propose that we should think of the twist in the following way. They tell us that a twist of type 2b supergravity on, for example, a Calabi-Yau fivefold can be defined. There is a suitable choice of Q which has the properties that I'll need for this talk. And the resulting theory is the Kodaira-Spencer theory on that Calabi-Yau manifold, which might be already familiar to many of you as the closed string field theory or the target space supergravity theory for the B model topological string. And of course, this was studied by Bershadsky, Ciccati, Oguri, and Vafa. So already we see this idea that of the simplifying power of performing these twists. On the supergravity side, our degrees of freedom included all components of the metric as fluctuating fields in the theory. Here, we're restricting to some simpler and more tractable set of degrees of freedom. And the Kodaira-Spencer theory in particular is a theory that governs deformations of the complex structure. So we retain some of the dependence of the metric fluctuations, but only precisely those that modify the complex structure. So we're working in a fairly, in a simpler and more tractable physical setup than the original theory. Okay, so we've assumed this conjecture, but in particular, everything I've said required that the background that we started with was Calabi-Yau. And so it seems like applying this directly to ADS 3 cross S3 cross T4 would be a little bit cumbersome. Or indeed, I haven't told you how one should do it. So to get around this complication, I propose that we do the following thing. Let's start life in 10 dimensions in our twisted theory and try to run in parallel the derivation of the ADS CFT correspondence exactly as we would do in the physical theory. And I'll sketch how that goes. And then the hope is that doing this twist and then following through the ADS CFT prescription are commuting processes. And hopefully this twisted model then will still capture salient features of the physical duality. So we'll run through this procedure, and then I'll explain some of the results or computations that one can do in Kodaira-Spencer theory in the aftermath, and we'll indeed see that the results we get from following this procedure seem to encapsulate some of the BPS physics of the full untwisted duality, which gives us confidence that this is a sensible procedure, and at bare minimum, it's giving us a nice toy model that we can approach mathematically. So let me remind you how this derivation goes, and we'll work in parallel between the physical and twisted duality, and I'll tell you what the result is. So as usual in the physical string theory, we start in 10 dimensions, and we'll consider type 2B string theory on R6 cross T4. I'll be in Euclidean signature throughout this entire talk. Correspondingly, we can start in Kodaira-Spencer theory on now C3 cross T4 equally well. So here, the twist that we're using is well defined. And to this system, we of course add our D-branes. In this particular example, one adds N1 D1 branes, wrapping a choice of 2-plane in R6, cross some points in T4, and N5 D5 branes, wrapping the same 2-plane in R6, and also wrapping all of the 4 torus. And similarly, one can add the same number of branes in the B model, now wrapping a complex plane, a choice of complex plane in C3. The next step is to perform the dimensional reduction on the 4 torus, so we can study the effective 6-dimensional gravitational theory that's coupled to an effective 2-dimensional theory coming from the non-compact directions of the brane world volume. We can do the dimensional reduction equally well in the physical and twisted theory, and on the next slide, I'll say a bit more about how that procedure works in this Kodaira-Spencer theory. But at the end of the day, one obtains, as I said, a 6-dimensional theory that's coupled to a theory of some effective strings given by these branes, and we'll define n as usual to be n1 times n5, so there's n effective strings in our theory. Now, crucially, the D-branes, of course, are massive charged objects. They couple to the closed string sector of the theory, and they will deform the geometry, as you all know. And in particular, the D1, D5 brane systems will source some Ramond-Ramond flux that will deform the metric in the transverse space to the branes, and one can compute this back reaction and obtain in a suitable limit the ADS3 cross S3 geometry that we're interested in. So we need to do a similar computation on the B model side. Indeed, the B branes will source a field that descends from this Ramond-Ramond flux, and it turns out that, as you might expect from the Kodaira-Spencer theory, it deforms not the full metric, of course, but the complex structure of the transverse flat space. It will do so in a way that's integrable away from the support of the branes, and will obtain a manifold that we call the Superconifold, which I'll describe in more detail on the next slide. And of course, to complete the derivation of this duality, there are various judicious limits that one has to take, which are expected to be trivial from the point of view of this cohomology. So for our point of view, and through much of the talk, I will keep in my mind the origin of this dual pair is really arising from a coupled open closed string system, since these decoupling limits, or the cohomology is not so sensitive to these decoupling limits. And this will be a useful perspective later, as I'll stress. Okay, so let me tell you a little bit more detail about what one obtains in the twisted theory, and in particular tell you how should you think of twisted to be supergravity on ADS3 cross S3 from this point of view? What's the resulting theory? Okay, so I claimed that the ultimate answer was Kodaira-Spencer theory on this manifold that I called the Superconifold, so let me tell you what that is and how we got there. So here we are starting life in our 10-dimensional flat space. The branes are wrapping some plane that I'm endowing with a coordinate, holomorphic coordinate z, and let's give the transverse coordinates, transverse planes the coordinates w1 and w2. And I also have my 4-dimensional torus. So first, what's the result of the dimensional reduction on the 4 torus? Well, to tell you that, let me remind you about some of the basic properties of Kodaira-Spencer theory. Kodaira-Spencer theory is a theory whose basic degrees of freedom are polyvector fields that satisfy an equation of motion and a constraint equation, and also potentially a gauge fixing condition. I'm suppressing the various equations, and I haven't written down the Lagrangian, but these are well known in the literature. And in particular, polyvector fields on some manifold are nothing but 0J forms valued in anti-symmetric powers of a holomorphic tangent bundle. So these are some basic geometric objects, and we're incorporating fields at all values of I and j, which for me is is equivalent to keeping the full BV-BRST complex of Kodaira-Spencer theory. So implicitly, although I'm not being very explicit about the ghost number and details in this talk, I'm including ghosts, antifields, and the like, and really keeping this full complex. And again, that will be a point that will be a little bit more important later in the talk. Okay, but nonetheless, I have this theory whose basic degrees of freedom are these polyvector fields. And since I'm on a Calabi-Yau manifold, well, any Calabi-Yau manifold has a non-vanishing holomorphic volume form. So if you don't like polyvector fields, or for technical convenience, you can always contract these polyvector fields with my holomorphic volume form on the Calabi-Yau, and equally well think of them as ordinary differential forms. So my Kodaira-Spencer theory is a theory governing some differential forms on my Calabi-Yau, and on a product space, the polyvector fields factorizes as products as well. So dimensional reduction, as usual, is going to be an instruction to keep only the massless field content of the theory, which in the twisted context is going to tell us that we should restrict to considering harmonic polyvector fields on T4, which by this isomorphism here tells us that we're keeping, well, harmonic forms. So in other words, when we do the dimensional reduction, we just pick up a factor of the cohomology ring of T4, and that will kind of come along for the ride in many of the computations. So the cohomology ring of T4 has 4 free generators, DZ1 through 4, and I'll just label them, I'll rename them as etas, just to emphasize that these are some anti-commuting variables. They're going to span this flat supermanifold if you wish. Okay, so that's the result of the dimensional reduction. And as I said, we need to understand the back reaction in this theory, or the deformation of complex structure that's induced from the presence of these branes. So the RR flux in this case turns out to descend to a special polyvector field, in particular a Beltrami differential, and the equations of motion and constraints tell us that this Beltrami differential is in fact an integrable complex structure deformation away from the support of the branes, preserving the volume form. And one can write down this Beltrami differential explicitly. It depends in particular on the etas, and it also depends on this brane charge F. So it's an element of H2T4 of length n. Remember, n was the number of branes we had in the theory. So I have some explicit expression for the Beltrami differential. As usual, in a deformation of complex structure, I'm adding it to my del bar operator, and now I can compute. So we have a new complex structure, and I should ask now, what are the functions that are holomorphic with respect to the deformed complex structure coming from this Beltrami differential? Well, given the Beltrami differential, you can just compute it. The W1 and W2 coordinates, holomorphic coordinates, are still good holomorphic coordinates, even in the presence of this new field. And you can also solve for these two other new good holomorphic coordinates that I'm calling U1 and U2, which depend on the F's, etas, and the other coordinates in the following way. And by multiplying things together, it's not that hard to see that these coordinates satisfy the following equation in C4/4. And this is the defining equation for the superconifold. So this is the main punchline, or the upshot of this derivation, that the analog of ADS3 cross S3 is going to be the superconifold for us. And we call it the superconifold because had there been just an ordinary number or parameter on the right-hand side here, this would be nothing but the equation for the deformed conifold. But instead, because of our particular setup that involved T4, we have a dependence on these anti-commuting variables and this F. So we have some anti-commuting thing on the right-hand side. So this is what we call the superconifold. And we always restrict to the locus where not all of these U's and W's are 0 at once. So this is the basic thing that we want to study. We can now just compute things about Kodaira-Spencer theory on the superconifold. And this is our twisted version of ADS. And we can start to make progress just studying this part of the duality. So I'm going to focus on the supergravity for most of this talk, and defer to later work some of the details about the twisted CFT side, or the vertex algebra side. Okay, so given this setup, what are some of the things one can compute with this theory? Well, first, there is one technical point that I want to emphasize from the outset, which turns out to make life very convenient computationally, and was also surprising to us when we first realized it. So before we took into account the complex structure deformation, this is our flat transverse space. We have C3 with the support of the branes removed, and we have this factor spanned by the etas coming from the dimensional reduction, which corresponds to setting F equal to 0. on the previous slide. That's the flat space answer. So if we had wanted to study Kodaira-Spencer theory in the absence of back reaction, that's the setup we would study. However, on the superconifold, we have these f's and etas on the right-hand side, and f cubed is quite clearly 0 in the cohomology ring of T4, which tells us that the effect of this back reaction can only correct flat space answers by a finite number of terms. So there's some kind of truncation happening here that would not happen, for example, in the ordinary deformed conifold, where you would get asymptotic series and in 1/n correcting the flat space relative to the back reacted answers. And again, this is going to be a huge boon for us computationally. Ordinarily, if we wanted to study this open closed string system, maybe we'd write down a vertex like this to approach things Feynman diagrammatically. Had we wanted to do perturbation theory, we'd have the brane coupling to some closed string fields in Kodaira-Spencer theory via this Beltrami differential. And a priori, you would expect that to capture something like a propagator in the back reacted geometry, you have to do some kind of resummation, or hope that you could, of some diagrams like this, where you would have a priori an infinite number of these flux legs correcting the computations. But here we can have at most 2 such legs if we wanted to compute such diagrams. So that's just something I want to stress, which I think a priori is surprising, but certainly quite nice for our purposes. Okay, so we have this Kodaira-Spencer theory that's somehow perturbatively close to flat space in a technical sense. And well, what are some of the properties that this theory has? In particular, one of the most basic things that you might want to determine are the single particle gravitational states in Kodaira-Spencer theory on this superconifold. So we'd like to enumerate all such states up to gauge equivalence and see what kind of answers we get, and in particular, if they comport with the physical with BPS states in the physical supergravity. So one can use geometric techniques to approach this problem. I won't give the details of these computations, but in particular, we closely follow some methods that were developed in a paper by Costello and Gaiotto, also studying an example of twisted holography. And many of the techniques they developed can just be adapted directly to this case. So I'll refer to that paper and our paper for the details of this kind of computation. The basic idea is to study a compactification of the superconifold, which has some explicit boundary geometry, and then ask, given my Kodaira-Spencer theory, I have some equations of motion, I can impose some natural vacuum boundary conditions on the fields, and I'd like to ask that the single particle gravitational states, as usual, should be dual to local violations of the vacuum boundary condition that otherwise satisfy the equations of motion and the boundary conditions everywhere except at isolated points. So again, one can do this analysis. Let me just tell you the upshots and the basic takeaways from what we find. So we find some particular states in Kodaira-Spencer theory that I'm going to name alpha, gamma, and some mu's. Alpha and gamma are fermionic fields, and the mu's are bosonic fields. So first of all, it turns out we can write explicit closed form expressions for these things. I haven't fully done it on this slide. And in particular, we're really aided and abetted by this truncation property from the previous slide. But I'll refer to the paper for the explicit expressions of these things. Importantly, all of these states turn out to be highest weight states for an SL2 and an SU2 algebra, which have natural geometric interpretations from this point of view. So they're represented by some vector fields on this boundary. You can act on the states and see that they're highest weight states of the listed quantum numbers here. Their descendants with respect to these algebras are also included. You can also write them down explicitly. They're part of the story. And all of these fields occur, as you might expect, with a multiplicity depending on the cohomology of T4, which again is technically coming along for the ride in all of these computations. And the key point here is that these states organize into some very familiar objects physically. They form certain multiplets. In particular, they form short multiplets with respect to the superalgebra PSU112. And this superalgebra is perhaps familiar to some of you as the global subalgebra of the n=4 superconformal algebra, which is enjoyed by the boundary CFT. In particular, in a holomorphic twist, the boundary CFT only has one holomorphic copy of n=4 superconformal algebra, and it has, so as its global subalgebra, one copy of PSU112. So these fields in a holomorphic twist are organizing themselves naturally into short multiplets, and this is reassuringly exactly what we expect to obtain from classic papers of de Boer and David Mandel-Wadia. So that is comforting, that our twisted theory indeed seems to be capturing information of a special subset of the untwisted theory. Here's another result about Kodaira-Spencer theory on the superconifold that you can prove geometrically. Again, I'll refer to the paper for the details of the proof, but it's not a hard result at all. So you can prove that there is a nice infinite dimensional symmetry algebra, in particular Lie algebra, acting as the symmetries of gauge symmetries that preserve the vacuum in this theory. And I'm working in the strict supergravity limit again, so this is a purely infinite n result. As a vector space, the algebra looks something like this. Maybe it looks a little bit forbidding, but it's explicitly described in terms of some very concrete geometric objects. You can also write down the commutators and anti-commutators completely explicitly. The interesting part is that the bosonic piece of this infinite dimensional algebra is the algebra of holomorphic divergence-free vector fields on the superconifold. This algebra is an algebra of symmetries of the superconifold. And here's some fermionic superpartners that I'm going to not worry about today. Okay, so this is our infinite dimensional Lie algebra. It acts as vacuum preserving gauge symmetries of my gravitational theory. Holographic duality then will suggest the following natural conjecture. What I have on one side must act somehow on the other side. So in particular, we conjecture that this Lie algebra should act on the chiral algebra of the sim-n-T4 superconformal field theory in the strict infinite n limit. And what this symmetry algebra is dual to is what's called the global symmetry algebra of the CFT, which are the symmetries that preserve the vacuum at 0 and infinity. So just as SL2 is the global symmetry algebra of Virasoro, just as PSU11/2 is the global symmetry algebra of the n=4 superconformal algebra, we conjecture that this infinite dimensional Lie algebra is the full global symmetry algebra of the full chiral algebra and the holomorphic twist. Good. So in particular, it must include PSU11/2 among the low-lying modes, because that's the global subalgebra of n=4. And indeed, you can explicitly find that algebra here, although I haven't shown it. But again, it's not a difficult computation. And it includes modes of all of the other fields, so it's much larger. In particular, it includes the appropriate modes of the alphas, gammas, and mu's of the previous slide. Just as a remark, this is a very nice geometric algebra. It's related to algebras of functions on the superconifold. Algebras of functions on the ordinary conifold have appeared previously in string theory, in work originally by Witten, and then in a line of thought that was pursued by others. And in that case, these algebra functions on the conifold arose as the ground ring in a certain non-critical string theory. So some degree 0 cohomology elements that generated an interesting and I think unexpected symmetry structure in a string theory. So just a remark or a question for the future is, could the ground ring of the ADS3 cross S3 cross T4 string perhaps be related to the algebra of functions on the superconifold? I think it would be nice to make connections between these objects, but that's just a question it's food for thought. So let me tell you the situation thus far, just to summarize some of these results. So far I've told you that studying twisted supergravity in the sense of Costello and Lie gives for our bulk or ADS theory, gravitational theory, Kodaira-Spencer theory on the superconifold, employing this twisted derivation. You can use algebrogeometric methods to enumerate the single particle states, and they organize themselves into precisely the representations expected from the familiar physical duality. And you can also determine the infinite n, or purely classical supergravity symmetry algebra, and it's determined in terms of geometric objects. So more generally, you would like to, at least at infinite n, start to study the full vertex algebra, not just its global symmetry subalgebra. And if one were to do this from the gravitational point of view, there's a prescription that one would follow. You would try to extract these OPE coefficients from Witten diagram computations in our Kodaira-Spencer theory, and then try to match them to 2- and 3-point functions in the twisted CFT. And it's a healthy exercise to do this, at least for some OPE coefficients, and I will not say anything more about that. It will appear in the future. And in particular, although you can do this and do this matching, it's a tedious procedure. Even in the holomorphic theory, it's a tedious and technically difficult procedure. So it's not really the front on which we want to push this the studies of this toy model. But okay, it seems that in our hands, we still have a nice toy example of the ADS-CFT correspondence. It seems so far to be amenable to rigorous formulation, at least then. The untwisted counterpart is well studied. And now for the remainder of the talk, what I'd like to do is try and ask what kind of mathematical structure we can really glean that's underlying this twisted duality and what can we learn from it. So this is the part of the talk where Koszul duality enters. And in particular, it's going to be useful for us to also obtain some results beyond the strictly planar limit, or in particular, we're going to be able to access 1/n corrections at the end of the day. And of course, part of the motivation for trying to study the mathematical structure here is we hope that some of these structures will be able to apply to or lend insight to at least twisted dual pairs a little bit more generally, perhaps even serving as a defining principle for these special examples. At least that's part of the hope, but to be determined. So what's Koszul duality? Well, it's some kind of operation that given an algebra A, one can obtain a different algebra A shriek. For the moment, A and A shriek should be thought of as differential graded associative algebras, or if you really wish, A infinity algebras. So they're algebras that are actually better thought of as complexes with a differential. A and A shriek share various nice properties. In particular, there are equivalences among their module categories that are very nice. But so given, the important point for right now is that given A, you can define a natural object A shriek, and I'll tell you that in fact it has a natural role to play in a physical system, that these Koszul dual pairs naturally emerge from a physical setup. So it's, at the moment, this seems like a little bit of an interlude, but I'll come back around to ADS-CFT shortly. So A shriek can be defined in terms of A in the following way. So let's say A is an algebra or a DG associative algebra over C, and we'll view C as a one-dimensional module for A, the ground ring of the algebra. Then A shriek is defined in terms of derived endomorphisms of this one-dimensional module that commute with the action of A. Or loosely speaking, there's some homomorphisms from C to itself, compatible or commuting with the action of this algebra. And you can see directly from this definition that indeed I'm really working with complexes. Even if A was an ordinary algebra supported in degree 0, A shriek kind of has no choice but to be a complex. Well, physically, I've already sort of anticipated where natural complexes might arise. We have BRST complexes, or in this context, twisted BV-BRST complexes, and we have a natural differential coming from our twisted BRST operator. And indeed, Koszul duality does appear in physics. In particular, it arises when one tries to couple topological line defects of order type to bulk quantum field theories. So what do I mean by that? Well, let's say I have a topological line in some quantum field theory, a topological direction, meaning that there's some operator in the theory whose anti-commutator with the BRST operator renders translation along that direction trivial in cohomology. So in other words, if I bring operators from my bulk theory to the support of this line or very close to it, they should acquire a structure of an associative algebra, because in the presence of the topological twist, I don't care what the precise positions of the operators are, I only care about their ordering. That's the structure for an associative algebra. The claim is that given defining A in that way, as that kind of associative algebra, naturally produces A shriek in terms of coupling this line defect to a bulk quantum field theory. So let me be precise about that now. So we say that A shriek is, if you wish, the algebra governing the universal line defect in my theory. What do I mean by that precisely? Well, a topological line defect of order type means I'm just trying to couple some topological quantum mechanics along the line to my bulk quantum field theory. And I wish to do so in a BRST invariant way, or in a way that's free from continuous gauge anomalies. So my topological quantum mechanics, it's my choice. A priori, it supports some arbitrary algebra of operators B that also has the structure of a DG associative algebra. And I claim that anomaly-free or BRST invariant couplings of the topological quantum mechanics to my bulk theory are in bijective correspondence with a choice of homomorphism from A shriek to B, where A shriek was defined on the previous slide. In other words, A shriek governs the symmetries that a defect theory needs to have to couple non-anomalously to my original theory. So just as when you go to a carnival and you see a sign that says, you must be this tall to ride this ride, A-shriek is telling you that whatever the generators of your B algebra are, whatever larger algebra or whatever algebra they fit into, they had better furnish a representation of A-shriek. They had better have at least that much symmetry in order to couple to my original theory along that topological line. The proof of this statement is in the paper. We proceed by a path integral argument. In the interest of time, I won't flesh out the details. But ultimately, these path integral manipulations produce for you a Moore-Cartan equation. And one is able to relate these possible couplings as a space of solution up to gauge equivalence to the Moore-Cartan equation of these tensor product algebra along the line. So here intuitively, we see something like, well, deformations of an uncoupled tensor product algebra will give us a space of possible consistent couplings. And you can make use of a very deep isomorphism in mathematics that tells us that this space is isomorphic to the Hom space, maps from the Koszul dual to B. Okay, so this is something general. Okay, that all seemed like perhaps a bit of an interlude. How do these ideas relate to the ADS-CFT example that I was discussing in the earlier part of the talk? Well, what I'd like to do is generalize this notion or propose a generalization of this notion of Koszul duality to the context of vertex algebras or differential graded vertex algebras. And let me do this physically by proposing an analog of the previous procedure to the vertex algebra context. So mathematically, this has only been formalized in some special examples by C. Lee, so it's something that hopefully we can work on with our mathematical colleagues. The basic idea is to make the obvious replacements. We go from a topological line to a holomorphic plane, an associative algebra to a vertex algebra, commutators become OPEs, and again, the line becomes a holomorphic plane. And then let me define now a Koszul dual algebra A-shriek as kind of the universal vertex algebra that can be coupled to my bulk theory along a holomorphic plane, such that there are homomorphisms of DG vertex algebras from A-shriek to B that govern the possible BRST invariant couplings along that plane. And well, why is this notion something I want to introduce? Because remember, in my twisted theory, this derivation was really remembering the origin of ADS-CFT as a coupled open closed string system. And at the most naive level, I can imagine my two-dimensional D-brane theory as defects of order type in flat space coupling to my closed string degrees of freedom. And remember, the twisted theory doesn't care so much about these precise decoupling limits. So the question is, given our now good understanding of the theory in the bulk, what we understand about Kodaira-Spencer theory on the superconifold, can we deduce something directly about the boundary chiral algebra, about our twisted SCFT, using this Koszul duality perspective by demanding the vanishing of anomalous couplings between the two? Now, of course, thinking of D-branes just as defects in the flat space theory is naive, and I will have to incorporate back reaction later, and it will deform the notion of Koszul duality that I need to use. Sorry, I see some chats, but I don't think it's easy for me to check them. So if it's a time warning,
yes,
yeah,
so
please.
I think you have officially 2 minutes.
2 minutes, okay.
5 minutes.
Great. Okay, yeah, thank you. I'll wrap up. Okay, so that was a fairly abstract thing that I've said so far. Of course, I believe that formalizing these things will be useful for many reasons, but at some point you just have to get down to brass tacks, and let's compute the chiral algebra or the Koszul dual algebra from my bulk theory, from my Kodaira-Spencer theory. Given A, I can compute A-shriek and vice versa. Let's do it physically. So I can write down general BRST invariant couplings between Kodaira-Spencer theory and a putative defect CFT. Here I've displayed one coupling one of these mu fields to some so far arbitrary some arbitrary defect operators J. In particular, some of these J's correspond to chiral primaries or highest weight states of those multiplets, just to orient the physicists that might be familiar with those operators. And let's, again, for the moment, pretend I can work in flat space and work at infinite n. Well, I can just associate Feynman rules to these couplings, write down Feynman diagrams, compute the BRST variation of the Feynman diagrams, demand that all these BRST variations cancel, so there's a net no anomaly, and ask what conditions those impose on the OPEs of the defect operators. So writing down such tree-level diagrams will correspond to computing the Koszul dual at infinite n. But in principle, you can also write down loop diagrams, compute quantum corrections. In general, we know there can be gauge anomalies at higher loop order, and these will deform the classical OPE to some quantum corrected algebra. So here I've just listed some tree-level diagrams, and I've displayed exactly what one gets from performing this computation at infinite n in flat space for these J operators. Oops. Oh, sorry. There we go. For these J operators. Again, of course, it's not the whole story, but we can compute. And the J's in particular give some nice superloop algebra that also has a nice geometric interpretation as well. And again, in principle, you do the same kind of computations for the other operators, and you can proceed at order by order in 1/n. This is my last technical slide, so never fear. I do have to tell you about back reaction because that should, again, modify the story in some way. D-branes are not just defects in flat space, they source fields that interact with my closed string theory. In particular, there's going to be some additional term in the bulk action that couples the Beltrami differential field to closed string fields in the Kodaira-Spencer theory. You can write it down and you can compute the BRST variation of that term, and it is non-vanishing. And it's non-vanishing precisely on the support of the D-branes. So previously what we had done is try to compute the vertex algebra or defect OPEs by demanding that the coupling of the defect to the bulk theory had vanishing anomaly. Now in the presence of back reaction, we also have to reckon with this term, but technically we can do the exact same thing. We just demand that the defect OPEs have an anomaly that precisely cancels that of the anomaly from this term, so that the total system, again, is BRST invariant. And there's a suitable Feynman rule, again, that one can write down for this term, and cartoonishly it looks like a vertex like this, where the Beltrami differential is coupling to the identity operator of the chiral algebra. And again, here, the beauty of this truncation saves us, because so far I had been working in flat space, but because f cubed is 0, there's only a finite number of new diagrams incorporating the back reaction that I need to write down at each order in 1/n. So life is fairly simple. In the n goes to infinity limit, it turns out that there's 3 classes of diagrams to compute. I'm just giving you the simplest one here. And in particular, this one centrally extends the algebra. And again, there's some other diagrams that you compute. So I think there's a hope because of the simplicity of this model and this truncation. You could hope that perhaps we can even prove some all orders results about the OPEs using homological algebra techniques, but doing so will require some interaction with mathematics and will in particular require formalizing this version of Koszul duality for DG vertex algebras. In the presence of back reaction, it should be some kind of version of curved Koszul duality, which roughly speaking adds a source to the Morar-Cartan equation. So now let me summarize and wrap up. So for this part of the talk, I've said that there's a version of curved Koszul duality for vertex algebras that comes from considering anomaly-free bulk defect couplings. You can compute the defect algebra from the bulk or vice versa, diagrammatically in order by order. And again, the key point is that the defect operators had better furnish a representation of my Koszul dual algebra. For BRST invariance, that's non-negotiable. So you are directly accessing at least some kind of universal part of the boundary chiral algebra by doing some computations with the bulk fields, which are some complex of ghosts and anti-fields, but you can work with them. In our ADS-CFT context in particular, if you fully incorporate the back reaction at infinite n, which I just gave you a small preview of, you can recover that geometric algebra we saw in the earlier part of the talk from this Koszul duality point of view, including these divergence-free vector fields. And again, in particular, that global subalgebra, our old friend, does appear in the low-lying modes. So that works nicely. And moving beyond the global subalgebra in particular produces, among the larger algebra, an n equals 4 superconformal algebra. I showed you how the central extension comes about. And one, of course, should and must move beyond infinite n, which involves, again, just computing finitely many new classes of diagrams, and hope to present some more results on that in the future. So that's what I wanted to tell you about today. I think this is just the beginning of a much larger story. And of course, there's, as with any story, there should be quite a lot of sequels, and there's much left to determine. So let me list some here. I don't think I'll, in the interest of time, since I've already gone over, I won't go through things explicitly. But for example, perhaps in Kodaira-Spencer theory, it would be very interesting to know if we could perhaps study some BPS black hole solutions, recover other aspects that are known from the boundary CFT from the Kodaira-Spencer point of view. It would be wonderful to connect the twisted supergravity perspective with various world sheet analyses that have been performed in recent years. There are a lot of beautiful results on that front that it would be great to connect to, and much more, including other examples. And again, towards at least an optimistic goal of proving special examples of the ADS-CFT correspondence. So thank you for your attention. Thanks for your patience since I went a little bit over time. And yeah, I'll take questions now.
Hey, thanks very much, Natalie, for this nice talk. I'll unmute everyone, and so please clap. And I will mute everyone again. So there are questions by, I think, Mykola Derushenko. You should be able to unmute yourself without me doing so.
Hi, Natalie. Nice talk. So I have a few questions, actually. So the first one is, from the point of view of Kodaira-Spencer theory, how do you determine the vacuum boundary conditions?
Oh, there are natural choices of those. It's part of a longer story. Again, the paper of Costello and Gaiotto has the most complete analysis that I would refer to for the details.
Yeah, I mean, I know they have this kind of logarithmic poles. I'm just wondering what kind of principle, physical and or mathematical, would allow you to fix those poles, for example?
So in particular, one has to ask that the interactions in Kodaira-Spencer theory are still well defined at the boundary, given the holomorphic coordinate system on the boundary and the form of the holomorphic volume form as one approaches the boundary. So given consistency conditions from that, one also has to show that there's a sensible propagator and various other things. So yeah, it's a bit intricate and involves, well, it incorporates in particular well-definedness of the interactions and bulk to boundary propagators. Although if Kevin and Davide want to chime in and add to that as well, please feel free.
Okay. Another question was about the 1/n corrections in the case of ordinary conifold. So what would be the simplest quantity to receive such? I mean, certainly the geometry itself, the background already satisfies Kodaira-Spencer equations, so it's exact, right? But what would be the quantity that receives, like the simplest example that receives 1/n corrections?
The simplest example that receives, well, so for example, I mean, we're computing 1/n corrections in the vertex algebra for this defect theory. Or do you mean something else? I mean, you could imagine doing scattering processes of these single particle gravitational states. Well, first of all, the form of the gravitational states themselves receives 1/n corrections. In our example, they truncate because of this f^= 0 property, but in the ordinary conifold, the form for the alphas, gammas, and mu's and so forth incorporate or involve 1/n corrections. Their scattering processes would involve 1/n corrections.
Okay, so the structure constants of the chiral algebra, basically.
Yeah, absolutely.
And one last question, similar actually in spirit. What would be the simplest example of Koszul duality in the chiral algebra? Like for associative algebras, probably one of the nicest examples are quadratic algebras, where you can explicitly describe the.
Absolutely, yeah. Quadratic algebras in the associative case are very nice.
So what about chiral?
The simplest, yeah, that's a good question. The simplest. In our paper, we do an example of holomorphic Trin-Simons theory, but I would hesitate to call that the simplest. It's just kind of a slightly simpler analog of the computation in the Kodaira-Spencer theory. Actually, there may be, I would refer to that paper by C. Lee that I cited earlier, who was working on formalizing this notion of Koszul duality for chiral algebras from a more Cartan point of view. And I'm blanking on some of the precise examples that he studied, but yeah, that's where I'd check.
Okay, Greg Moore has a question. Greg, if you can unmute yourself.
Hi, Natalie.
Hi.
Hi. So, yeah, I had a question about this equivalence between the Morey-Cartan elements of A tensor B and the Hom from A shriek to B.
Mhm.
Does that mean that the set of Morey-Cartan elements is a linear space?
The set of more Cartan elements is a linear.
Well, Hom A shriek, well, at least the way I was thinking, maybe you mean, I don't know what you mean by Hom, but I assumed you meant by homomorphisms of algebras.
Mm-hmm. Yeah.
Right. That's a linear space. I think of the Morey-Cartan elements as sets of solutions to a highly nonlinear equation. So I don't think of that as a linear space. So I was a little confused by that.
Good. Maybe let me think about that a little bit and get back to you.
So another question about that statement is that were A and B algebras or A infinity algebras?
You can think of them as A infinity algebras. I was thinking of them as BG associative algebras, augmented algebras actually, which is something I suppressed. Okay,
because taking a tensor product of two general A infinity algebras is not a trivial thing at all. In fact, it's a moduli space of tensor products.
Yeah. So
the moduli space would have to show up on the other side.
Yeah. So in that isomorphism, I was lying a little bit for simplicity. In the context of A infinity algebras, yes, you, strictly speaking, rather than A tensor B, you have actually the augmentation of ideal of A tensored with B.
But still,
yeah, there are many things I swept under the rug, but I think actually sorry.
But the notion of what I'm getting at is the notion of a tensor product of A infinity algebras is non-trivial. And in fact, there's not really a canonical tensor product.
Yeah, I was being a little bit sloppy there. There's actually the subtleties of that definition, I think, were discussed nicely and fairly recently in a paper by Gayotto and O.
Okay.
But yeah, indeed, that equation that I presented should be viewed as a cartoon, and we can discuss.
And last question about that equation. So you want to generalize algebras to vertex algebras, did I?
Yeah, so I need...
By vertex algebra, you mean vertex operator algebra?
Not necessarily. I just mean some differential graded vertex algebra. I don't think I need the extra conditions from a VOA. Okay. But I do need to tell you what MC of A tensor B is, and it's not really on that side. It's not a tensor product of vertex algebras. You should define some suitable Lie algebra related to that tensor product. Again, it hasn't been fully formalized except by Seeley in special examples, but the basic idea is that given those uncoupled vertex algebras, you should define some kind of Lie algebra that, roughly speaking, is going to be from looking at the coefficients of 1 over z in the OPE and quotienting out by total derivatives. So you have to define a suitable Lie algebra from the tensor product from the vertex algebras. Otherwise, that thing doesn't make sense, and I haven't told you how to do it, and it hasn't been done in general. Only in examples.
Okay, thank you.
Okay, Koszul, you have a question.
Yes, very nice talk, Natalie.
Thank you.
The conifold, the superconifold that you had depended on Fij, which I guess is related to the B fields on T4, correct?
Yeah, it's essentially the brain charge. So the integral of f squared over C0/4, the direction spanned by the etas, is n. So it's just encoding the flux of the d brains.
Oh, just the flux. So
just the flux.
So it's discrete parameters for you.
Yeah. Well, so since I'm working in classic. Oh,
right. So the main question is motivated by where does the moduli of T4 enter your story?
The moduli of T4 essentially don't enter my story. The Kodaira-Spencer theory was only, so first of all, it's only sensitive to the cohomology of T4. So I really only use kind of the basic, like the Poincare pairing and the cup product in H star of T4. And since I'm working classically, it's H2 of T4C. So the dependence on T4 is that of just perturbative classical supergravity. There's not any finer information retained after I do the dimensional reduction.
So, I see. So it seems to me that there are two possible views of topological theories applied to this example, ADS3 times S3 times T4. One is viewing ADS3 times S3 as if it's a Calabi threefold, and viewing T4 as the extra space, which is so it's reversing the order of what we usually do.
Yeah.
Which is fine, and I think that's closer to what you are, the viewpoint you have taken, at least closer to the viewpoint you're presenting here. There's another viewpoint, which is you start with the theory on T4. And in that context, the theory has more supersymmetry than Calabi-Yau. And it's natural in that case to do the n equals to 4 topological string version of it, which is not Collier-Spencer theory, but gives you a self-glow gravity in 4 dimensions as the corresponding theory. So there would be a generalization of that presumably for these extra ingredients that you're introducing, but in that theory, it will depend on the modular of T4 and all the other.
Yeah.
So I'm curious to know if you have had any thoughts about that other topological twist.
No, I mean, that's an excellent point. One slightly related thing that I've thought about, but don't have anything too concrete to say about is that one could also, as you said, we can start from the theory of branes on T4. Now, view that as a gauge theory in the ADHM sense, in which case N1 and N5 start being treated asymmetrically as opposed to completely symmetrically as they are from our point of view. You could study a twist of that gauge theory, which should now, treat N1 and N5 differently. And, sort of how does that theory differ or remain similar to the analysis that we did, which is dual to the pure supergravity point. I guess that was a long-winded way of saying, like, that is an excellent point that I wish I could say more about. It's indeed something to think about and should be physically very instructive for understanding these examples better. I agree, but unfortunately don't have too much more to say at the moment. It would be great to make the connection more.
Okay, I don't see any other questions. So I think we close the session. Let's thank Natalie again. Unmute all.
Thanks, everyone.
And I think Jeff presumably will take over now. So I'll leave you with Jeff. Thanks, Natalie.
Thank you very much, Sakura and Natalie, and I really appreciate the background. Let me thank the speakers for the day and also the session chairs for the day. I have been assigning people to the breakaway rooms in the background, and I'll still do so for anyone who has any preferences to go to session 1, which will be the first 3 speakers for the day, or session 2, which would be Tom and Natalie in their session. The speakers will be assigned automatically to their sessions so that they can answer questions and things like that. I'd like to take the opportunity to encourage students in particular to go to the breakaway rooms and ask questions. It would be a good experience to interact with the speakers. So if you could please just tell me your preferences for which session to go to. I will include that and then open the rooms on the hour, and I'll keep them open for an hour, after which we'll close for the day. So thank you very much to the speakers again and the session chairs, and let me know your preferences, and you should get an invitation to go to a particular breakout room on the hour.